What's up, everybody? It's Dan from SageMathTutoring.com, and I'm back helping a student with some high-level probability stuff, university-level probability stuff. I understand that this might be hard to read. The problems that are forthcoming will be less hard to read, so just bear with me. I'll read this, and that way we can all be on the same page here. But anyway, high-level probability, or higher-level probability at least. Let's say university-level probability is what we're going to cover. Okay, so a bag contains four $1 bills. I'm going to write that down. Four $1 bills. All right, now I'm going to call that D. Okay. Three $5 bills. So there's three Fs. That's $5 bills. And two $10 bills. I'm going to call that T. Okay, so we have T, F, and D. An experiment consists of drawing three random bills from the bag simultaneously. Thus, the experiment has 9 choose 3 outcomes, 84 equally likely outcomes in the sample space. What's the probability that at most one $5 bill is drawn, given that no $10 bills were drawn? So ultimately, what we're trying to find is conditional probability. So we are trying to find the following fraction. Okay, the probability that at most we could say 1F, at most one $5 bill, given that no T, or we could say T prime. Okay, so great, and that is the following formula. It's going to be the probability of at most 1F intersected with no 10 all over the probability of no 10. Okay. Now, in my view, the best way to go is to focus on the denominator first. Just figure this part out first. The question is, what is the probability of no 10? Well, just in general, if we were to pull, let's see, we're drawing three random bills. We know that the probability of not getting a 10 would be such that the denominator is 84, because they already told us there's 84 equally likely outcomes in the sample space in general. So all the possible outcomes would be, there'd be 84 total possible outcomes. But then when we analyze, well, what are the target outcomes where we don't have a $10 bill? Well, I think the target outcomes would consist of the following scenarios. One target outcome is that you have three $1 bills, and we're going to be adding that to another possible outcome. We're going to find out all the different ways this can happen. We're going to be adding that to another possible outcome where you have three $5 bills, and then you're going to be adding that to another outcome where you're going to have one $1 bill and two $5 bills, and then you're going to be adding that to another outcome where you have two $1 bills and one $5 bill. Now, keep in mind, this is all combination problem stuff, because this order doesn't matter, all right? The order by which you are, pulling out the dollar bills doesn't matter. And one giveaway for the record that the order doesn't matter is this word simultaneously here, okay? They say simultaneously. We're drawing simultaneous, which means you're reaching in the bag and you're using your hand and you're grabbing three bills and you're just pulling them out at the same time. Whenever they use the word simultaneous, that's code for combination problem as opposed to permutation. Now, the question is, how many ways can we pull three $1 bills out simultaneously? Well, that would be, I like to use this notation for combinations. That would be 4 total $1 bills, choose 3. All right, and then we're going to be adding that. So how many different ways can we pull 3 $5 bills when there is already 3 $5 bills in there? Well, that would be 3 total $5 bills, choose 3. And then we're going to be adding that to the scenario of pulling one $1 bill and 2 $5 bills. So that would be 4 choose 1 times, and as far as these 2 $5 bills, that would be 3 choose 2, and then we would be adding, let's see, 4 choose 2 times 3 choose 1 for all the same reasons. Now, you could always use your calculator to figure out what these are. Now, I could already kind of tell what this is going to be. This is going to be 4 times 3 times 2 over 3 times 2 times 1. And that's going to end up being just a 4. And then we're going to be adding that to, I'll make this actually red. This is 4. And then we're going to be adding that to 1. There's only one way to choose 3 from 3. Then we're going to be adding that to 4 choose 1, which is just 4. And 3 choose 2. That would be 3 times 2 over 2 times 1. So this is going to be 3. Then we're going to be adding that to 4 choose 2. Well, 4 choose 2, that would be 2 times 1, and 4 times 3. That would cancel with that, and then we'd have 6. So that would be 6 right there, and then 3 choose 1 is just 3. Okay, so that's what we have so far. Now, let's take a look a little more closely. That would be, let's see, 4 plus 1, 4 plus 1 is 5, obviously. That's 12 plus 18. 12 plus 18 is 30, and that would be 35. All right, so 35 right there. Okay, so we just found the probability of no t. It's 35 over 84. Now, I do believe, is that reducible? I think it is. Maybe they're both divisible by 7. 84 divided by 7. 12. Okay. So it looks like that's going to be 7 over 12. Now, for those of you watching at home, if you catch me making a careless mistake, just let me know in the comments. But pretty sure this is going to be 7 over 12. Yeah, 35 divided by, oh, no, it should be 5 over 12. Oop, I just caught myself. That's going to be 5 over 12. So that's going to be 5 over 12. 35 divided by 7 is 5. 84 divided by 7 is 12. So that should be the denominator at least, right? That should be the denominator. So down there, we have 5 twelfths. But now what we're looking for is the intersection of at most one f and no t, right? Well, my thought is, what are the possibilities there? What are the possibilities there? At most one f and no t. Well, it's possible if it's at most one f, there's really 2 broad scenarios. There's either 0 f's or there's 1 f, right? So, you know, those are possibilities adhering to these restrictions. So let's think about the 0 f's. But we want to take into account no t as well, right? Well, in order to have 0 f's but also no t, I think the only way to make that happen is if you have 3 d's, right? I'm pretty sure. So this is the only scenario where you could have 0 f's with no t's. So I'm going to even write no t up here just to help. Okay. I think that's the only scenario that satisfies 0 Fs and no Ts, is if you get three $1 bills. Now, what about if you get one F and no T's? Well, that would be F, that would be FDD, I think, right? That would be FDD. You know, that would be one F and two D's. I think that's the only way, that's the only outcome where there's one F and no T's. So when analyzing the intersection, the probability of this, what that's going to turn out to be is the following yellow box, which I'm going to bring over here. Well, the possible outcomes we already know is 84. But then we need to figure out, you know, the desired outcomes that adhere to these restrictions. Well, the desired outcome that adheres to those restrictions is the DDD outcome. And we're going to find out how many ways that can happen. And we're going to add that to the FDD outcome. And we're going to analyze how many different ways that can happen. Well, the good news is over here, we already found out that there are 4 ways that DDD can happen. So that's going to be 4. And then FDD, we found out that DDF over here, we found out that there's 18 ways that that can happen. So therefore, what we're really dealing with is 22 over 84, which is 11 over 42. So that is the numerator, 11 over 42. Now again, for those of you at home, if you catch me making a careless mistake, please let me know. But I don't think I'm wrong about any of this. Now this would be 11 over 42 times 12 over 5. Also, for those of you at home, if you can see, if you can very quickly see an easier way of going about these, let me know. This is divisible by 2 for sure. This is divisible by 2. And then we would have ultimately 66 over 21 times 5, which is 105. That reduces to 22 over 35. Okay, so again, pretty sure that's right. For my student at home, just know that, you know, this is the overarching formula that you're going to need. You kind of go on a separate mission to figure out the denominator separately and then the numerator separately. And I think the key is to not get overwhelmed by just focusing on one thing at a time. Recognize that this is the entire war, but there's these little miniature like battles that need to be won before you win the war. You have to figure out, you have to win this battle off to the side, and you have to win this battle off to the side. Notice how I'm using letters. That's going to be really helpful. You really think about, well, what are the scenarios that adhere to the restrictions? You know, these are the scenarios that adhere to the restrictions. And then recognize that those desired scenarios are going to go in the numerator, where all possible scenarios are going to go in the denominator. Okay, Rihanna has 7 background dancers for her performance at the Grammys. 5 are wearing black costumes, so I'm going to call that 5 black costumes, 5B. 2 are wearing white costumes, so that's 2W. If 2 of the dancers, choosing 2, 2 of the dancers are selected at random to join Rihanna on stage for the encore, what's the probability that at least one will be wearing black, given that at least one is wearing white? At least one is wearing black, given that at least one is wearing white. Okay, I'm going to use the formula just in case. There's a part of me that wants to do a little shortcut type thing, but I'd rather stick with the script, which is what I think my teacher wants, or I think my student's teacher wants, I should say. I'm going to stick with the protocol of relying on that formula just in case. So let's see what happens. So 7 background dancers, choosing 2, probability that at least one will be wearing black, at least one B, given that at least one is wearing white, at least one white, and then that's going to be the probability of at least one B intersected with at least one white, all over the probability of at least one white. Okay. So, again, I'm a fan of figuring out the denominator first. We are going to go on a separate mission called Find Out the Denominator, the probability of at least one white. So how many general possibilities are there when choosing 2 dancers from 7 dancers? Well, that would be 7 choose 2, which we're going to worry about later. How many of those feature at least one W? Well, that would be, let's see, WW scenario plus the WB scenario. Yeah, yeah. So this scenario would be 2 choose 2, because there's 2 white dress dancers, and we'd be choosing 2 from that pool, and we're going to be adding 2 choose 1 times 5 choose 1 right there. Now, I say we take this over here. So that would be 7 choose 2. Well, 7 choose 2 is really 2 times 1 down below, 7 times 6 up top, and that's going to equal 21. So down below, we're going to have 21. Now, let's think about this. 2 choose 2, that's going to turn out to be 1. 2 choose 1 is 2. 5 choose 1 is 5, so that's going to be 2 times 5, which is 10. So that's going to be 1 plus 10, and that's going to be literally 11 over 21. So far we are successfully piecing this together. That is 11 over 21, unless I made a careless mistake, in which case, please, for those of you watching, let me know. It's the last time I'll say that. Don't worry. All right, probability of at least one B and at least one W. So I'm going to go off to the side. We're going to think about that also. We're going to use green to color code that scenario. We're going to focus on all the ways that both of these restrictions can happen at the same time. Well, the only way this restriction can happen is if it's BW, right? BW. And let's just pause and think about that. Isn't that the only scenario that conforms to this restriction? If you're choosing 2 dancers, the only way to adhere to the restriction of at least one B and at least one W has to be BW. Now remember, the order doesn't matter here, okay? As long as there's one black dress dancer and one white dress dancer, then doesn't matter what the order is. We've adhered to this restriction. right? So this represents the desired outcome, and that's going to be over all possible outcomes. And we figured out that all possible outcomes is 21. So then the question is, how many different ways are there to get BW? Well, we already figured that out down here. There's 10 ways of getting BW, right? 10 ways of getting BW. So that is, therefore, the numerator. That's the probability of getting at least one B and at least one W. That's the probability of it. It's 10 out of 21. So this fraction divided by this fraction would reduce to 10 out of 11. So in my opinion, this problem highlights the necessity of having faith in this formula, because some students might think, okay, well, there's 21 ways that we could choose two dancers from a pool of 7. And clearly, if we're looking for at least one B and at least one W, well, it's just going to be BW over 21. And then I think a lot of students might make the mistake of thinking that that's actually the answer. But it's not. Since it's conditional, you have to realize that this is the formula you need. It's kind of weird. It's a bit of a mind bender. But just know that anytime they use the word given, it's conditional, and you're going to want to rely on this. Okay, a box contains 10 chocolates, 4 with pecans, so I'm going to write that 4P, 5 with coconut, 5C, 1 with raspberry, 1R. Supergirl eats 3 of the chocolates. All right, so we're choosing 3, chosen randomly. If it's known that at least one of the ones she eats has coconut, what's the probability exactly one of them has coconut? So again, this is conditional. So anytime they use the word given, you should know that it's conditional. But also, anytime they use the phrase, if it's already known something, that means if it's given at least one, blah, 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 right? So that means what we're trying to find is that the probability, they say, what's the probability of exactly one coconut? Exactly one is coconut, given what we already know. Well, what do we already know? At least one is coconut. All right, now for my student at home, just know that I know this equation sucks, okay? It's ugly, it's disgusting, it doesn't look nice, it's annoying to write. It's sort of the first step of a long journey of potential complications and potential careless mistakes. Like, I get all that, but unless you use it, it's going to be very hard to figure this out, because this is I mean, just think about this logically. If it's known that at least one of the ones she eats has coconut, what's the probability that exactly one, right? Like, without this tried and true formula, that's going to be very challenging to wrap your head around, okay? So we want to use these equations. So this is the probability of exactly one coconut intersected with at least one coconut. And that's going to be easy to find out, by the way. And then we have, that's going to be all over the probability of at least one coconut. Well, guess what I'm going to do? Focus on the darn denominator first. Here we go. Focusing on the denominator it up. Okay, the probability of at least one coconut. What are all the ways we could choose 3 chocolates just in general from 10 total chocolates? Well, that would be the denominator. That would be 10 choose 3, which we're going to worry about later. And the probability of, let me just make it clear what we're doing. It's the probability of at least one C, at least one coconut, at least one C. Okay, so we know the denominator is going to be all the possible ways we could choose 3 chocolates from the 10 total chocolates. That's going to be 10 choose 3. Now we want the probability of at least one C. So let's take into account all the possible scenarios. I like to write these on the numerator, as you may have noticed. Well, there's a possibility of 3 C's, right? And we're going to be adding that to the possibility of all the possibility of 2 C's, right? So that's going to be CCR plus CCP. Right? And then we're going to be adding that to all the ways you could have one coconut. So that would be C, let's see, CPP plus CPR, I believe, right? Because there's only one R. I think these are the only 2 ways that you could have, the only 2 outcomes that feature one coconut. Okay. So these are all the outcomes that feature one coconut. These are all the outcomes that feature 2 coconuts. And these are all the outcomes that feature 3 coconuts. And in that, we're satisfying at least one C. Now, there is another way we could kind of reason this through. We could find out how many possible ways are there to choose 3 chocolates just in general. That's 10 choose 3. And then we could subtract from that all the ways that we could choose no C's, right? But in my opinion, that's kind of roundabout. That's unnecessarily roundabout. I'd rather just focus on the exact desired outcome. There's the possibility of 1 C, there's the possibility of 2 C's, and then there's the possibility of 3 C's. So we're going to analyze each of these separately. This would be something choose 3. That would be 5 choose 3. And we're going to be adding that to 5 choose 2 times 1 choose 1. We're going to be adding that to 5 choose 2 times 4 choose 1. And we're going to be adding that to 5 choose 1 to 4 choose 2. We're going to be adding that to 5 choose 1 to 4 choose 1 to 1 choose 1. I'm going to save room by doing all this here. So 5 choose 3, that would be 5 times 4 times 3, 3 times 2 times 1. So let's see, 3, 2, 1, 5, 4, 3, cancel, 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 that would be 10. Okay, so that's 10 plus 5 choose 2, let's see, 2 times 1, 5 times 4, that's also going to be 10 times 1, so I'm not going to worry about this. 1 choose 1 is just 1. 5 times 2, 5 choose 2 we already did. That's going to turn out to be 10, and that's going to be 10 times. 4 choose 1 is 4. We're going to be adding that to 5 choose and 4 choose 2. 4 choose 2. That would be 6. We're going to be adding that to 5 times 4 times 1. Okay. So that's clearly 10 plus 10 plus 40 plus 30 plus 20. And that's going to be all over 10 choose 3. Now I know it's getting messy, so I'm going to kind of go off to the side. Let's just remind ourselves that even though it's gotten messy, I mean, we're still dealing with the same thing. Let's figure out 10 choose 3. 10 choose 3 would be 3, 2, 1, 10, 9, 8. The 9 would cancel with the 3. The 10 would cancel with the 2. So that would be 40 times 3, which is 120. Okay, so that down there is going to be 120. 10 choose 3 is 120, and then we're going to have to add all these. That's going to be 50 plus 40 is 90. That's 100. That's 110. Okay, so that's the probability of at least one C, unless I made a careless mistake, which is always a possibility, but I don't think I did. Okay, so we got 11 over 12 ultimately, right? You could reduce it. Okay, now we want to analyze the intersection of exactly one C and at least one C. Well, isn't the restriction just exactly one C? Right? Isn't that what it is? So, I don't know. With that, you could go figure out, well, how many total possibilities are there just in general? Well, we already figured that out. That's 120 total ways that we could choose 3 from 10 chocolates, right? And now we want to take into account, in the numerator here, we want to take into account only the ones that feature both exactly one C and at least one C. I kind of feel like we did that over here, didn't we? So once you do the denominator, the numerator so far is turning out to be pretty easy. These are all the ways that you can get exactly one C, right? So that's going to be 30 plus 20, which is 50. And that turns out to be 5 over 12. So this is going to be down here, 5 over 12. And that would reduce to 5 over 11. So I do believe that's the answer to that one. Okay, Page Turner loves finite mathematics. This is their way of being funny, just for the record. Page Turner, ha 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 ha, loves finite mathematics. Oh, okay, that's the name of the class. I got it. All right, she has 6 books about probability, 5 books about matrices. Pardon me, I'm sorry. These things are predictable. All right, 6 probability books, 5 matrices books. She tells her friend, I need a tutor. I need a tutor. She lends her friend 4 of the books selected completely randomly. Okay, so choose 4. Choose 4. Okay. What's the probability Paige lends Anita 2 books on each topic, given that she lends her at least 1 book on each topic? Okay, so once again, rely religiously on the darn formula. It's going to be the probability that lends 2 books on each topic, given that lends at least 1 book on each topic. So I know my student at home is probably like, what the heck, man? I don't want to do all this, but it's character builder, I guess, right? We'll call that A. We'll call that B. So probability of A and B. Okay. The probability of B. I'm tired of writing all this out, to be honest. So once again, starting with the old denominator, probability of lending at least 1 book on each topic. Probability of lending at least 1 on each topic. Okay, well, what are all the ways that you could choose 4 from 11? Well, that's the denominator, which we're going to worry about later. So what are all the ways that you could have at least 1 in each topic? Well, that would be M triple P plus double M double P, right? plus triple M P. And I think that's it. I think that is actually it. Those are all the ways that you could have at least one on each topic. So when analyzing all the ways the first scenario could happen, that's going to be something, choose something. This is going to be the ones pertaining to the probability. We're going to be adding another combination here and another combination there. So with regards to the matrix books, that's always going to be a 5 on top. I'm actually just going to get that over with. When it comes to the probability books, that's always going to be a 6 on top. I'm going to get that over with. All right, 5 choose 1, 6 choose 3, 5 choose 2, 6 choose 2, 5 choose 3, 6 choose 1. Okay, 5 choose 1 is 5. So that's going to be 5 times 6 choose 3. So 3 times 2 times 1, 6 times 5 times 4, canceling, canceling. So that's going to be 20. Plus 5 choose 2, 5 choose 2, 2 times 1, 5 times 4, cancel. That's going to be 10. That's 10 times 6 choose 2, 6 choose 2, 2 times 1, 6 times 5, cancel. 3 times 5 is 15. We're going to be adding that to 5 choose 3. 5 choose 3 is 3 times 2 times 1, 5 times 4 times 3, cancel, 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 cancel. That's going to be 10 again. 6 choose 1 is just 6. 5 times 20 is, of course, 100 plus 150 plus 60. I do believe that is going to be 310 at the end of the day. Let's actually just call it that because we know that it's that. Okay, 11 choose 4. What is that? 4, 3, 2, 1, 11, 10, 9, 8. Cancel, cancel, cancel. 5 times 2 is 10. 10 times 3 is 30. 30 times 11 is 330. Reducing this fraction gives us 31 over 33. So congratulations to me. I just found the denominator of the overarching fraction. Now, we want the probability of at least 2 books on each topic and at least 1 book on each topic. Or lens. Okay, we want the probability of 2 books on each topic and the probability, the intersection of that, and the probability of at least 1 book on each topic. Well, this already satisfies that. So this is the bigger, more strict restriction. So I'm only going to pay attention to that. So what is the probability of at least 2 books on 1 topic? Well, we already know that there's 330 total ways of choosing 4 from 11, so that's going to be the denominator, right? And we want to only know the probability of having 2 books on each topic, which is going to once again be MMPP, right? Because doesn't that satisfy both of these conditions? And we want to satisfy both of the conditions right now. Doesn't that satisfy both of these conditions? MMPP. That's the only combination that does satisfy both of those conditions. And we already found out what MMPP is. It's 150. So it's 150 over 330. That should be a 0, 330. So that is 15 over 33. 15 over 33. And that is going to turn into 15 over 31. So that's how you would work that one out. Suppose A is all this. A subset of A is selected at random, i.e. all subsets equal chance of being selected. If the subset is not empty, what's the probability it contains the element B? All right, so that's conditional. Probability that it contains the element B. Given that it's not empty. Well, once again, religiously relying on the formula. Okay, so starting with the denominator, probability of not empty. So how many total subsets can you get from this? Well, that's going to be 2 raised to 1, 2, 3, 4, 5, 6, 7. 2 raised to the 7th power. And then one of these is going to be the empty set. So the probability, the desired outcomes, all the subsets that are not the empty set are going to be 2 to the 7th minus 1. Okay, so this is the first time where it actually makes sense to go about things in a roundabout fashion. You know, all of the subsets that are not empty would be represented by this number. That's all the possible subsets minus the empty set. So that's going to be the following. 128 on the bottom, and therefore 127 up top. So this one turned out to be not too bad, right, compared to some of the other ones, in that we just found our denominator at least, right? It's that 127 over 128. But now we want to know how many of these sets contain B, and it's not the empty set. Well, it's not the empty set. Well, it's already the case that if it contains B, it's not empty. So therefore, we really just need to pay attention to, you know, what's the probability that it contains B? Because it's implied that if it contains B, it's already implied that it's not empty. So this is the sort of more strict restriction that we need to pay attention to. So what is the probability that it contains B? Well, that would be a separate process that we'll kind of work out up here. Probability that contains B. The subset contains B. Well, the denominator of that probability would be all possible subsets, which is 2 to the 7th, which we already know is 128, but we'll just put 2 to the 7th. And then we want all the ones that contain B.
Well, my thought is, if we want to know how many of the subsets contain B, and how many elements do we have? We have 7 elements, right? I already figured that out. So there's 7 elements. What if we did all possible subsets? And then we simply subtracted the ones, all the subsets, the number of subsets that don't contain B. So how many subsets don't contain B? Well, wouldn't that be all the subsets that could be formed by these 6? I'll say that again. How many subsets could be formed that don't contain B from this? Well, wouldn't that be all the subsets containing these guys? And only these guys? I think so. So let's realize that the number of subsets that don't contain B is 2 to the 6th. Okay, so down here we have 128. We already knew that. And this is going to be 128 minus 2 to the 6th, which is 64. And that's going to be 64 over 128, aka 1/2. So that's going to be 1/2 up there. Okay, so that would reduce to 64 over 127. So how many, if all the subsets have an equal chance of being selected, the subset is not empty, what's the probability it contains the element B? That would be 64 out of 127. Okay, so this one's a weirdly abstract one. The experiment has a sample space of all this with all outcomes equally likely. Consider events E, which I guess means the chances of choosing ACE from this bucket, and event F, which is the event of choosing these elements from this bucket. So this first one would be clearly the probability of E and F, the intersection all over the probability of F. So the probability of picking F would be 3 over 6, aka 1/2. And the probability of both E and F, well, what is the intersection of these two? What do they have in common, in other words? Looks like what they have in common is most definitely a C and most definitely the E, right? So the probability of getting the intersection of E and F, well, there are 2 elements in that intersection, and there are 6 total elements to choose from. So that would be 2 over 6, aka 1/3. So it's 1/3 over 1/2, and that would become 2/3. All right, so hopefully that makes sense. You could always pause it, rewind it if need be. The probability of E given F prime, well, that would be the probability of E intersection of those things over the probability of F prime. Well, the probability of not F is once again going to be 3 over 6, aka 1/2. Now, the probability of getting both E and not F, that basically means the element that they don't have in common, the element in E that is not in common with F. All right, now F has D, so we don't care about D. We don't want C, D, or E, but we do want as much of E as possible without having F. Well, that would be this one here. So that's one, only element A satisfies this restriction. So that's going to be 1/6. 1 out of 6 elements in the sample space. So that's going to turn into 1/3. Okay. The probability of E prime intersected with F, the probability of F down below. Well, the probability of F we already know is 1/2. So we want the restriction that says nothing from E, but as much as possible from F. So we don't want any of the things in common. We only want this D right here. Okay, we only want that D, because that's in F, but not in E. So that's going to be, once again, 1/6 and that should turn into 1/3. Okay, and then the probability of E prime given F prime would be the probability of this intersection over the probability of not F. So down below, we already know that that will be 1/2, and the probability of both not end E, the probability of getting an element that is not in E nor is it in F, well, let's see, ACE, CDE. I think the only element that's not in E or F is B. So that's going to be 1/6. And 1/6 over 1/2 is once again 1/3. Okay. Pretty sure I'm right about that. Yeah, D, C is represented both. Yeah, pretty sure I'm right about that. B is the only one. Now keep in mind, for my student at home, remember, I'm going to bring this up here. To say not prime, E prime and F prime, well, that's the same thing as saying not the union of these. All right. So to say not E prime, to say not E and not F, not E and not F is the same thing as saying not E or F. All right. So if you have to think about that, go ahead. But associate this with and, associate this with or. This is essentially saying not E and not F, which is the same thing as saying not E or F. All right, that's De Morgan's law. So that's that. Okay, used car has 8 Hondas. All right, I'm going to write that. 8 H, 4 of which have new tires. 10 Kias, 4 of which have new tires. 18 Toyotas. Okay. All right. I'm seeing the value already of creating a table. We have Hondas, we have Kias, we have Toyotas. And then we have this other phenomenon called new tires and not new tires. No new tires. I'll just say no. No new tires. Okay? And whenever I make a table like this, I've always kind of seen that it's helpful to get the totals included. That usually will come into play. Now the total amount of cars, just period. We'll see, total. The total amount of cars, period, goes down here. And that's going to be 8 plus 10, which is 18, plus another 18. So that's going to be 36. All right, now I have experience, so I'm seeing that there's 3 different kinds of cars, and in each category, there's 2 subcategories. So whenever you have this overarching category with subcategories, you might want to consider some kind of a table. All right. Now there's 8 total Hondas. So I'm just going to put there 4 of which have new tires. I'm going to fill out the information. There's 10 Kias, 4 of which have new tires. There's 18 Toyotas, 10 of which have new tires. 10 of which have new tires. So what that means is we could fill out these totals as well. This right here is going to be 18. 10 plus 4 plus 4. This is going to be 4. This is going to be 6. This is going to be 8. So that's going to be 18. Okay. Now, I strongly suspect that this table is going to be fairly helpful for this problem. So let's take a look at it. What's the probability of H given N? Okay, H be the event that the car is a Honda. K is the event that the car is a Kia. T, the event that the car is a Toyota. And N be the event that the car has new tires. Okay, N is the event that the car has new tires. So just to kind of stay in line with their terminology, I'm going to call that N, and I'm going to call this N prime. Now, I don't see any N prime, so it looks like we're not going to have to worry about that, but that's okay. Well, diving into the fray, we're going to look at this one first. So we know that that's going to be the probability of both H and N all over the probability of just N. So what's the probability of just N? That's going to be 18 over 36. So that is 1/2 down there. And what's the probability of getting both H and N? Well, that would be 4 out of 36. That would be 4 out of 36. So that's going to be, AKA, what's 4 out of 36? 1/9? 1/9. So that's going to be 2 over 9. 2 over 9. Okay. Pause the video, work it out if need be. But that's 2 over 9. What is the probability of N given H? Well, that would be the probability of N and H all over the probability of just H. Now, the probability of just H, according to the table, is 8 out of 36, aka 4 out of 18, aka 2/9. Okay? And the probability of both new and Honda is once again this. That's 4 out of 36, aka 1/9. Now that would reduce to 1/2. 1/2. Okay. Let's see. The probability of K given H, well, that is going to be the probability of K and H all over the probability of just H. Now the probability of just H is 2/9, and the probability of K and H is 0, because you cannot, only one car is selected at random, so you can't choose both a Kia and a Honda, so that's 0. Trying to be tricky with us, see that? You don't want to let them get away with that. So, probability of not T, N. Okay, so that's going to be the probability of T prime and N over the probability of just N. Now we already know that the probability of just N is 1/2. Now, the probability of not T, or T prime, would be these. Either a Honda or a Kia, so that's 18 over 36. Right? So basically it means not T, this is code for either a Honda or a Kia, but we want them to also be new. So that's going to be these. It's either a Honda or a Kia, but also new. So that's 8 out of 36. aka, was that 2/9? I can't remember. 8 out of 36. So that's going to be 2/9. Yeah. So that right there is going to be 4/9. All right, 4/9. Okay, so hopefully that makes sense. And my student at home might be recognizing that there is a way to get fancy as long as you have the table. I strongly recommend you construct a table if you have categories and then categories within categories like that. Okay? And once you have the table, then you can kind of see that whenever it's asking, for example, for the probability of h given n, you want the n row or column to be the denominator. Whatever's over here on the right is the row or column that's going to be the denominator. So in this case, n is the row, and that's the denominator, 18. And then we're looking at h out of that 18. So that number tells you what row or column to focus on, and that tells you which specific cell to focus on. So we have 18, so that's going to be 4/18, which reduces to 2/9, and that's another way of getting it. This could have been the column for h, but we're only paying attention to the new, so that's going to be 4/8. This is a column and another column. You're not allowed to choose two columns at once, so that's 0. This highlights the row of n, which is 18 right here, 18 things. And then we're interested in not t. Well, that's going to be 8 out of 18 things. That's going to be 8/18, which reduces to 4/9. Okay, so for my student at home, if you want to get fancy, fine. As long as you have a table, go ahead. Recognize that the second value, second symbol tells you which row or column to focus on, and then the left-hand one tells you which particular cell to focus on. I think that would work every time. Now, if you're ever in doubt, what we have seen clearly is that this will work. A diplomatic team consists of 8 Australians, including Dame Edna. So that's one person. And 5 New Zealanders, including this person. The team must select 2 members to serve as officers. One is spokesperson, the other is chairperson. Okay, since the positions are different, this isn't just like creating teams of 2. The positions are different, which means we are going to be dealing with a scenario where the order matters, right? We have, let's say the first person is the spokesperson, and then the next person is the chairperson. Now there's 13 total people, right? So how many different ways can we pick from 13 people, one to be the spokesperson and the other to be the chairperson? That's going to be 13 times 12. And that is 156. So there's 156 potential ways that we could have one of these 13 people as spokesperson and chairman. Now you might be wondering, why does the order matter here? I don't get it. Well, think about it. Imagine you have people named A, B, C, D, E, F, G, and H. And we're picking one person for the spokesperson and the other person for the chairperson. Well, imagine we just pick A and B, or A and D rather, right? Well, that's a possibility, right? But isn't that a different scenario than this? It's the same 2 people, but the scenario is different, right? The scenario is different. So anytime the scenario will be different, even with the same 2 people, that means the order matters. The order by which you list the people matters, okay? So, let me get rid of that. So therefore, there are 156 different ways we could choose spokesperson and chairperson from the 13 people. All right. Select two members. Okay. What's the probability that this person is the chairperson given that this person is the spokesperson? Well, that's one of those things where it's going to be annoying to write, but whatever. It's going to be the probability. I'm going to call Dame Edna. I'm going to call that person D. So D is chairperson, given that S is spokesperson, and that's going to be P of D is chair, intersected with S is spokes, all over the probability that S is spokesperson. So focusing on the bottom part first, probability that S is the spokesperson. Well, there are 156 different ways to choose the teams of two, right? Now, how many different ways would include S as the spokesperson? You know, meaning Stephen Peter Kearney. Well, let's imagine this is the spokesperson position, and this is the chair. Well, there would be one possibility for the spokesperson, and then once that person is filled, how many possibilities are left over for the chair people? Well, 12. Right? 12. So, the answer there is going to be 12 over 156, and that reduces to 1 over 13. So we now know that the bottom is 1 over 13. So now we want to focus on the probability that D is chair and S is the spokesperson. Well, we already know there's 156 total possible teams. But there's only one way where D could be the chair and S is the spokesperson. There's only one scenario where that's true. So that's 1 over 156. So that's going to be 1 over 156 here. And that turns into, if you work that out, that's going to be 13 over 156. And 13 over 156 would reduce to 1/12. All right. So there's only one scenario out of all 156. There's only one scenario where S is the spokesperson and D is the chairperson. All right, what's the probability that D is the chairperson given that S is not the spokesperson? Okay. So we are going to bring that up here. And we know that that's the probability D is chair, given that S not spokes. So we already know that that would be the probability S is not spokes. And then up here, it's going to be the probability of the intersection of D is chair and S is not spokes. So focusing on this part now. Probability that S is not spokes. We already know there are 156 possible teams. How many of those feature S not being the spokesperson? Well, there's the chairperson, there's the spokesperson, I'll say, and the chairperson. Well, how many possibilities are there if S is not allowed to be the spokesperson? Well, there would be 12 possibilities for that, right? But then imagine we already put the person in the spokesperson position. We already chose from one of the 12. How many are left over for the chair position? Well, there's now 12 left over. So that's going to be 12 times 12, which is 144 over 156. And that reduces to 12 over 13. Okay, so already we know that this denominator, all right, we're going to bring this over here. The denominator is 12 over 13. But now we want to take into account the probability that D is the chair and S is not the spokes, right? What's the probability of that? Well, once again, we already know there are 156 total ways, or total teams that could be made. How many of those feature D as the chair and S as not the spokes? Well, I'm going to call this the spokes. I'll call this the chair. Now, whenever there's a bigger restriction, I always like to focus there first. So there's only one possibility for the chair. It's D, so we're going to put 1 there. Once we've chosen that, how many possibilities are there for the spokes? Well, D is already here, right? But we want to make sure that S is not the spoke. So it's not 12 possibilities, there's only 11 possibilities now, right? If the only restriction was that D has to be the chair, there would be 1 here and 12 there. But since S is not allowed to be the spokes, there's only 11 possibilities here, which means that this is 11 times 1. So out of all 156 possible teams, only 11 feature a scenario where D is the chair and S is not the spokesperson. Okay? I don't think that's reducible now. So that's going to be 11 over 156. And that would be, of course, over 12 over 13. That's a 13. And this whole thing would reduce to 11 over 144. Isn't this fun? Not at all. Okay, so 11 over 144. Okay. What's the probability that both officers are New Zealanders given that they are both from the same country? Okay, so probability both NZ for New Zealanders, given that they're both from the same country. Well, that would clearly be the probability both New Zealander and both same country. The greater restriction is this one, so we're only going to need to worry about this probability. But we do need to figure out what is the probability that both are from the same country. Well, once again, I know when I say once again, it's predictable and therefore perhaps annoying, but let's go with it. So probability that they're both from the same country, well, once again, there's 156 total ways of constructing the team. So what are the possibilities that they're both from the same country? Well, we need to find all the ways in which it's New Zealand, New Zealand, and all the ways in which it's, what is it? Australia, Australia, right? So New Zealand, New Zealand, and Australia, Australia. Now, my view is that the order should still matter here because it's still two separate positions. So even if they're both from New Zealand, the order matters because even if we choose the same two New Zealanders, there's a difference between one New Zealander being, the chairperson and the other New Zealander being a spokesperson and vice versa. Okay, so my strong belief, and I could be wrong, I don't know, comment below if I'm wrong about this, but my strong belief is even in this scenario, if we're trying to find out the probability that both are in the same country, because the positions are different, we still want to treat the order as something that matters. So therefore, we still have the spokesperson and the chairperson position. And as far as New Zealanders, well, how many New Zealanders are there? There's 5 of them. So you have 5 times 4 right here. And then over here, you also have the spokesperson and the chairperson. How many Australians are there? There's 8, so this is going to be 8 times 7. Okay, so 5 times 4 is clearly 20, and then 8 times 7 is clearly 56. So that, I believe, is going to be the fraction for the bottom. We're going to have 156 on the bottom, and we will have 76 up top, and that reduces to 19 over 39. Okay, so on the bottom we know it's 19 over 39. Now we need to figure out what's the probability that they're both New Zealanders and both from the same country. Well, if they're both from New Zealand, it's implied they're both from the same country, so we can kind of ignore that part and just focus on, well, what's the probability of them both being New Zealanders? Well, that's going to be 20 over 156, right? Probability that they're both New Zealanders, 20 over 156. Okay, now if you were to have 20 over 156 divided by 19 over 39, you would get 5 over 19. Okay, 5 over 19. So, pretty sure that's the answer. 5 over 19. Hopefully that helps. Hopefully these are right. But something like that reasoning process is definitely correct. Okay, so once again, they're giving us the car problem with the new tires and so on. So I'm going to go ahead and make that table. We have H for Hondas, we have K for Kias, and we have T for Toyotas. We're also taking into account the scenario of new tires and not new tires, right? And then we also want the totals. So let's look at it. 10 Hondas total. So that's at least the Hondas, 10. 35 Kias. 50 Toyotas. How many total cars is that? That's 95 total cars. Okay. One of the Hondas has new tires. 1. 7 of the Kias have new tires. 7. 11 of the Toyotas have new tires. Great. So 1 plus 7 is 8, plus 11 is 19. This would be 9. This right here would be 28. This right here would be 39. And this right here would be 76. Okay. Let H be the event that the car is a Honda, K be the event that the car is a Kia, T is the event that the car is a Toyota, and N be the event that the car has new tires. 2 events, E and F, are independent when the intersection of E and F are the probability of E times the probability of F. Are H and K independent? Well, I think we should use the test that they gave us. The probability of H and K, is that equal to the probability of H times the probability of K? Well, I don't know. The probability of picking H out of the lot is 10 over 95 times the probability of K would be 35 over 95, right? But you and I both know, you the listener and me the whiteboard person, we both know that the probability of picking both H and K is impossible because we're only picking one car. So that's a big fat 0, which means this does not equal that, which means they are not independent. All right, unless I'm making a mistake with the reasoning. Applying this test shows that they're not independent. Are H and N independent? Well, I'm going to say let's apply the test. Probability of H and N. Is it the case that that's the same thing as the probability of H times the probability of N? Well, the probability of H is 10 over 95. And the probability of N is 19 over 95. So that's going to be some ridiculous number. But let's just think about it. What's the probability of H and N? Well, that's right here. That's 1 out of 95. Do those things equal each other? Heck no. Therefore, they are not independent. Okay. Are K and N independent? This would be a very similar process. Okay. This would be a very similar process. Well, let's just do it. So probability K and N. Is it the case that that's the same thing as the probability of K times the probability of N? Well, the probability of K, picking K out of the parking lot, is 35 over 95. The probability of picking N out of the parking lot is 19 over 95. But we know the probability of picking both K and N is right here. That's 7 out of 95. Are they going to be the same? No. So that's no. Are N and T independent? So looking at that, I do believe it's going to be a very similar situation, but let's find out just in case. Probability of N and T. Is that the same thing as the probability of N times the probability of T? Well, the probability of N is 19 over 95. The probability of T is 50 over 95. And the probability of N over T, or N and T rather, would be that. That would be 11 over 95. Yeah, that is not true either. So those are not independent. So pretty sure that's right. The only one I feel a little weird about is this first one. Yeah, it's that first one, but again, H represents picking the Honda, K represents picking the Kia, because a car is selected at random. So the probability of picking a Honda and a Kia at the same time is 0. So yeah, I'm going to stick with that. I'm going to stick to my guns with that one. All right, so that's that. Okay, 2 ordinary fair-sided die are rolled. Okay, what's the probability? The sum of the numbers on the 2 dice is 6, given that the number on at least one of the dice is 3. Okay, well, pretty straightforward according to the problems we've been doing. So it's the probability sum is 6 given that the number on at least one die is 3. Okay. At least one die shows 3. Okay. Well, we're going to work that out. So let's see. That would be the probability sum 6 and at least 1 is 3 all over the probability that at least 1 is 3. Okay, so the bottom is what we should focus on first. Let's see, the probability that at least 1 is 3. Well, how many different outcomes can you get just period? How many different outcomes can you get in general? Well, that's going to be 36 possible outcomes, right? There's 6 possible outcomes for the first roll, and there's 6 possible outcomes for the second roll. So that's going to be 36 total outcomes. Now, how many of them feature 3 on at least one of the rolls? Well, there's the one that features 3 on the first roll, and then any on all the ones that feature 3 in the first roll and any on the second roll. There's all the ones that feature any on the first roll and 3 on the second roll, and then there's that one scenario where it's 3 and 3, right? 3 and 3. So this would be one possibility for the first roll being 3 times 6 possibilities for the second roll being any. This would be 6 possibilities for the first roll being any times 1 possibility for the second roll being 3. And this would be 1 possibility for the first roll being 3 and 1 possibility for the second roll being 3. Okay, so hopefully my student at home is following my sort of symbology. This represents the 3 cases where at least one of the 2 rolls is 3, right? So this is 6, this is 6, and this is 1, and then you could add them all up, and that's going to be 13 over 36. So that one belongs in the denominator. That belongs in the denominator, 13 over 36. But now we want to analyze what's the probability of the sum being 6 and at least 1 being 3. So we know there's 36 possibilities in general, but how many feature at least 1 being 3 and the sum being 6? Well, here's all the ones where at least 1 is 3. There's only one case in this scenario where, well, you know what? It's looking like if at least 1 is 3, then the other one has to be 3 in order for it to be a sum of 6. And I do believe there's only one scenario where that happens, right? There's only one scenario where they're both 3. Out of all 36 possible, outcomes from rolling 2 die, only one of those outcomes features 3 and 3, right? So that would be 1 right there. So therefore, this would have 1 over 36 there, and that would reduce to 1 over 13. Okay. 1 over 13. So let's see. What's the probability the sum of the numbers on the 2 dice is 8, given that the number on at least one of the dice is 3? Okay, so that would be probability sum is 8, given that the number on at least one is 3. So that would be the probability of sum is 8 and 1 is 3, all over the probability that 1 is 3. Well, focusing on the bottom first, we know there's 36 total outcomes. The probability that, at least 1 is 3, right? My bad. At least. And at least. Okay, so the probability of at least 1 is 3, I feel like we already did that. Did we already do that? Yeah, we already did that. That's 13 over 36, right? Okay, so we already did that. That's good. So that goes in the denominator. So we have 13 over 36 in the denominator. Now, what about the probability that the sum is 8 and at least 1 is 3? Well, wouldn't that be the following scenario where there's 36 total outcomes, and we want to take into account at least 1 is 3. Well, if the sum is also 8, then one die is showing a 3 and the other showing a 5, and then the other case would be where the first die is showing 5 and the other die is showing 3. Now that's not to be confused with 35 and 53. That's not to be confused with 3 times 5 or 5 times 3. That has to do with the results. Okay, the result of the first dice is 3, the second dice is 5, the result of the first die is 5, and the second die is 3. So that's literally 2 possible scenarios where you're going to have at least 1 is 3, but also the sum is 8 at the same time. So I'm going to replace that with a 2 because there's only 2 ways that can happen. Or we could say there's 2 outcomes that fulfill that criteria, right? So it's 2 over 36. So that means that this fraction is going to be 2 over 36. And that is going to be 2 over 13. Okay, I'm pretty sure that's that one. Okay, probability of the sum of the numbers on the 2 dice is 7, given that it is not 3. Okay. The probability, the sum of the 2 numbers. Yeah, kind of a weird wording, right? When they say it, I'm assuming they mean the sum. So if we want the probability that the sum of the numbers on the 2 dice is 7, given that the sum is not 3, well, of course the sum's not 3 because the sum is 7, right? So part of me wants to do a shortcut, but the other part of me wants to rely on the formula just in case I'm missing something. So let's take a look. Probability, the sum of the numbers on the 2 dice is 7. Sum is 7. Given that the sum is not 3. Okay, I'll go with it, whatever. Okay, let's just shorten things. We're going to call that A, call that B. So we want the probability of A and B all over the probability of B, which is the probability that the sum is not B, or not 3 rather. Well, there's 36 potential outcomes, and all the outcomes that feature 3, or I should say a sum of 3, there's only 2 possibilities. That's if dice 1 and dice 2 have the following rolls. Dice 1 could have a value of 1, dice 2 could have a value of 2, that would add up to 3, and it could be vice versa, that would add up to 3, but that's only 2 scenarios where the sum could be 3. So the probability of the sum not being 3 is going to be 36 minus 2, minus those two scenarios, which is 34. So that's going to be 17 over 18. Okay, so on the bottom, we should have 17 over 18. Now, what's the probability that the sum is 7 and not 3? Well, the greater restriction, well, if the sum is 7, it's implied that the sum is not 3. So what is the probability that the sum is 7? Well, there are 36 total outcomes. How many of them feature a sum of 7? Well, there's 1 and 6. That's a scenario. Another is 2 and 5. 2 and 5. There's 3 and 4. 4 and 3. 5 and 2. And 6 and 1, right? If that's dice 1, dice 2, dice 1, dice 2, dice 1, dice 2, right? So that's how many scenarios? 1, 2, 3, 4, 5, 6. So 6 out of 36 would give you a sum of 7, right? A sum of 7. So it's going to be 6 over 36 over 17 over 18. Now, 17 over 18 used to be 34 over 36. So this is going to reduce to 6 over 34. 6 over 34. AKA 3 over 17. So I hope that is correct. There's always a chance of a careless mistake, but once again, I do not think I made one. Hopefully that makes sense, though. Okay, probability, exactly one of the dice shows the number 1, given that the sum of the numbers is 7. So even before I try to wrap my head around this, I'm going to go ahead and set up the equation. I'm just going to cut to the chase. We're going to say it's the probability exactly one of the dice shows the number 1. And the sum of the numbers is 7. So honestly, I don't even care if I can wrap my head around it. I'm just going to write the formula and rely on the formula. So probability of the sum is 7. I feel like maybe we did that already, right? Did we already find out that the sum is 7? Did we do that already? Probability that the sum of the numbers, 2 dice, is 7. Yeah, that was 6 over 36. Yeah, that was 6 over 36. So this is going to be 6 over 36. I'm not going to reduce. I'm just going to leave it because this might have a 36 underneath it as well. So what's the probability that the sum is 7, but exactly one dice shows 1? Well, the sum is 7. So these are all the ones where the sum is 7. There's 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So there's 6 potential dice rolls that would sum to 7, right? But 2 of them feature exactly 1. So the probability of fulfilling this criteria, this strict criteria, you need to take into account that there's 36 total possibilities, right? 36 total possibilities for the outcomes of the 2 dice rolls, but only 2 of them satisfy this criteria. So that's going to be 2 over 36. So this becomes 2 over 36 over 6 over 36, which turns into 2 over 6, which turns into 1/3. So hopefully that makes sense for my student at home. Watch the video as many times as you need. Follow the thought process. Obviously using that formula is huge. Will you have to go off to the side and do the separate stuff? Absolutely. Just remember there's a probability on the bottom, there's a probability on the top. Both probabilities that you need to find for the denominator or the numerator of this sort of equation will require you understanding how many possible outcomes there are in the sample in general. Okay, so for example, 36 possible outcomes for 2 dice rolls, right? 36 possible outcomes for 2 dice rolls. So when you're working out these probabilities separately, you always need to remember that, and then you just work it out. You should end up with a fraction over another fraction, and then you reduce. Okay? Even if you are tempted to try a mental shortcut or do it in a fancy way, I would advise you to actually not do that. I would advise you to just simply rely on the formula. You'd be surprised that this formula turns out to be necessary and useful, even during times when maybe it seems like it shouldn't be necessary and useful. So I'm just going to give you that sort of, I don't know if it's a word of caution or what have you, but try not to get too fancy just yet. All right. So anyway, that is how you do all that stuff. For those of you at home, not my student, hopefully you got something out of it, and I will talk to you later. Bye.